So last week we covered the theory for this chapter, chapter 7, and we used the theory to apply it to nonlinear systems in dynamics. And so I'm just going to go over the theory very briefly, and then we'll go through and do some of the more complex examples that are in your notes. So as you know, this chapter deals with energy. Okay, up to now we've been using Newton's second law to find equations of motions for system. Now we're going to be using energy, and we're going to be using something called Lagrange's equation, which is this equation at the bottom down here, to find the equation of motion. Okay. L is known as the Lagrangian, okay, and that is simply the kinetic energy, T, minus the potential energy. And then by finding various differentials of L, you can find these two terms, and R, which is the energy associated with damping, and you find the derivative of that with respect to the velocity, you can end up getting an equation, and that equation will turn out to be the equation of motion. Now last week we went through an example in the notes that was linear, and we showed you that you get the same result whether you use the quick method from chapter 5 or whether you use this method, you get the same answer for the various matrices. But obviously, like I said, the big advantage of this is it can be applied to nonlinear systems where it gets much more complicated to use Newton's second law. So the process you go through is you find your kinetic energy, your potential energy, and your dissipation function R, and you compute the Lagrangian based upon T and V. You then take the derivative of the Lagrangian with respect to the variable you're interested in, that could be x or theta or whatever, but it's the velocity of that variable, okay, theta dot or x dot. And then once you've got that, you then take the time derivative and of that expression, and you get the first term in the Lagrangian equation. You then take the derivative of the Lagrangian with respect to that variable itself, so x or theta. And that will give you the second term. And then if you have damping in the system, r is not 0, then you take it with respect to that velocity and you get the third term in the equation. And you plumb them all in together, and out should pop your equation of motion. So, the problem we'll do first is we'll do question 3, which is this double pendulum. Okay, so there's the problem. We've got a double pendulum. Each of these is that's L1 and L2. There's going to be lots of subscripts in this problem. Okay, so I'll try and make sure I get them all right. And essentially we've got a double pendulum. So we've got one pendulum that comes down to M1 of length L1 and of angle theta 1, and then attached to the bottom of that is another pendulum, okay, L2. At the bottom of that we've got a bob M2 and an angle theta 2. And what we need to do is we need to find the equation of motion for this very nonlinear system, okay? And so that's what we're going to do. Now, what we do for the first one, for the first M1, we employ the same logic that we used when we did the single pendulum problem last week, where you find the position of the pendulum, you then take the derivative to get the velocity, and once you've got the velocity, you can then use mv squared, 1/2 mv squared, to get the kinetic energy. So that's what we're going to do first. And so the position of bob 1, x1, y1, which are the coordinates, okay, well, if y is upwards, okay, and x is, this is the origin, x is to the right, x is going to be very simply L1 sine of theta 1, and y1 is going to be minus, because it's y is upwards, so it's minus L1 cosine of theta 1. Okay? So that gives us the position of bob 1. We then find the first derivative with respect to time to get velocity, x1 dot and y1 dot. And if you take the derivative of this, you get L1 theta 1 dot cosine of theta 1. And then obviously for this one we have L1 theta 1 dot. Obviously the derivative of cosine is minus sine, so that gets rid of the minus sign. And we have sine of theta 1. That gives us the velocity. Great. That's step 1. So T1, which is going to be the kinetic energy of the first mass on its own, is simply 1/2 m1 x1 dot squared plus 1/2 m1 y1 dot squared. Okay, 1/2 mv squared in both the x and the y direction. That will be the energy of that bob on its own. And so we can plug in these terms, this one and this one, into x1 dot and y1 dot, and we get the solution. So let's do that. 1/2 m1, and then we've got L1 squared theta 1 dot squared cosine squared theta 1 plus 1/2 m1 L1 squared theta 1 dot squared sine squared theta 1. And since we know that cosine squared of an angle plus sine squared of an angle is 1, we can simplify that out. 1/2 m1 L1 squared theta 1 dot squared cosine squared of theta 1 plus sine squared of theta 1. And we know that that term is 1. So T1 is 1/2 m1 L1 squared theta 1 dot squared. Nice and straightforward. Okay, so now we've got to deal with the second mass. Now, the thing is, because the second mass, the position of the second mass depends partly on the first mass, what we're going to do is we're going to find the relative position of the second mass with respect to the first mass. And then we have to add the motion of the first mass on to get the complete motion of the second mass. And so the first step is to find the relative position of the second mass. So that's why I've written x2, y2, and then REL, relative, as a subscript, and that will give us the relative position of the second mass. And so that's very straightforward. We take this as the datum, set this point here, okay, y is upwards, x is to the right, and so we have to write, it's going to be very similar to what we wrote for the first mass, but instead we have L2 sine of theta 2 minus L2 cosine of theta 2. And so hence, x2 dot and y2 dot relative is almost exactly the same as what we had before. L2 theta 2 dot cosine of theta 2, and then L2 theta 2 dot sine of theta 2. And that gives us our relative velocities of that mass. And so to get the absolute velocities, x2 dot and y2 dot, and here I've written absolute, ABS. Obviously this is going to be x1 dot plus x2 dot REL, and x1 dot, y1 dot y2 REL dot. Okay, where this term we can get from x1 and y1, which is up here, okay, and obviously that term is this one here, and this term is this one here, and so let's do that. Let's stick it in. x1 dot is L1 theta 1 dot cosine of theta 1 plus L2 theta 2 dot cosine of theta 2. There's the velocity in x for the first one, and then we have L1 theta 1 dot sine of theta 1 plus L2 theta 2 dot sine of theta 2. Okay, so the kinetic energy for the second mass is going to be 1/2 m2, which is the weight of the second mass, times by the absolute velocity squared. I missed the squared out, apologies. Plus 1/2 m2 times the y velocity squared, the absolute y velocity squared. And so we have to take these terms, these ones here, this one here, and square it, and this one here and square it, and stick them in for those two terms. That's what I'm going to do. So let's just find x2 dot absolute squared. Let's just find that on its own. And so we have, obviously this is two terms, so we have got to multiply the first term, you square it, so that becomes θ1 dot squared cosine of squared θ1, okay, plus the second term squared, so that's L2 squared θ2 dot squared cosine squared θ2, and then you have 2 plus 2 times by them multiplied together, so we have L1 L2 θ1 dot θ2 dot cosine θ1 cosine of θ2. y2 absolute dot squared, we can follow the similar logic. L1 squared, θ1 squared, and then we have sine squared θ1, plus L2 squared, θ2 dot squared, sine squared θ2, plus 2 L1 L2 θ1 dot θ2 dot sine θ1 sine of θ2. If you think about it, this is relatively simple algebra, there's just lots of terms. And so if we go back to T2, 1/2 m2, that's multiplied by both of them, so let's just not worry about the other one. And let's group them together. We can see that we've got this term plus this term. Okay, well there's a cosine squared and a sine squared, that we know is 1, so we've got this term here, L1 squared, θ1 dot squared, and then that's multiplied by cosine squared θ1 plus sine squared θ1, which we know is 1. Then with the second term, these two terms, again we've got a cosine squared plus a sine squared, so we could do the same thing, L2 squared, θ2 dot squared, and then we've got cosine squared θ2 plus sine squared θ2. Again, we know that's 1, so that drops out. Yes, that should be squared, indeed. That should be squared. Apologies, yes, there's a few squares missing. There we are. Thank you. Shows you're paying attention. So yeah, obviously these two terms, that one, that one, that one, and that one, and that one, and that one, those theta dots should be squared. Make sure they are. And so we have to deal with these last two terms. Well, again, they're common with the exception of these trigonometric terms. So we could write this out as plus 2 L1 L2 θ1 dot θ2 dot, and then in brackets cosine of θ1 cosine of θ2 plus sine of θ1 sine of θ2. Now if you're hot on your trigonometry and you remember some of these, you'll notice that this can be contracted down to cosine of θ1 minus θ2. Now I should put some of these identities on your equation sheet if they're not already there, and if you need them. Okay. If this question was on the exam, I'd give you that identity so you knew on the equation sheet. And so we can write this down very simply. T2 is 1/2 m2 times by L1 squared θ1 dot squared plus L2 squared theta 2 dot squared plus 2 L1 L2 theta 1 dot theta 2 dot cosine of theta 1 minus theta 2. Okay, and this makes sense because if you think about it, we've got the kinetic energy of mass 1, which is that one, okay, plus the kinetic energy of mass 2 on its own, plus some contributory factor between mass 1 and 2 that takes into account the fact that it's moving in relation to it, okay, and so that's the kinetic energy of mass 2 on its own. So obviously T total is going to be T1 plus T2, and so we can write that out very simply, 1/2 m1 L1 squared theta 1 dot squared plus 1/2 m2 L1 squared theta 1 dot squared plus 1/2 m2 L2 squared theta 2 dot squared. That should be squared, by the way, apologies. Plus m2 L1 L2 theta 1 dot theta 2 dot, then cosine of theta 1 minus theta 2. Okay, so that's the kinetic energy of the two bobs. We now have to find the potential energy. Okay, for easier. There's no spring, so it's just gravitational energy. And so we've got mgh for both of the masses. So we've got m minus, okay, because h is downwards, m1, g1, and then we have L1 cosine of theta 1 minus m2 g, I don't know why I've written g1, there's only one g, m2g, and then this is multiplied by L1 cosine of theta 1 plus L2 cosine of theta 2. And if we go back to this drawing, okay, so I'll leave that up there, but we go back to the drawing, you can see that h in this case, okay, for this one we've got the vertical distance is L1 cosine of theta 1, okay, so that's this term here, minus because it's downwards, y is upwards, so it's downwards, that's minus. And then for this one we've got m2, which is down here, and we've got this distance plus this distance. So it's L1 cosine of theta 1, which is this distance here, and then we've got this distance down here, L2 cosine of theta 2. Again, it's minus because y is upwards. Has everybody got this top equation? Yeah? Please holler if I take it away and you still need it. Okay. And so that's L. We don't need to worry too much about having to change it. We could multiply this out if we wanted to, so let's do that just to make life a little bit easier. M1 G L1 cosine of theta 1 minus M2 G L1 cosine of theta 1 minus M2 G L2 cosine of theta 2. So L is T minus V, so let's take T. This becomes a little bit ugly, but let's do it. 1/2 M1 L1 squared theta 1 dot squared plus 1/2 M2, sorry, L1 theta 2 theta 1 dot squared plus 1/2 M2 L2 squared theta 2 dot squared plus M2 L1 L2 theta 1 dot theta 2 dot cosine of theta 1 minus theta 2, and then minus this. So this becomes plus M1 G L1 cosine of theta 1 plus M2 G L1 cosine of theta 1 plus M2 G L2 cosine of theta 2. Ugly. And let's set our generalized coordinates. We'll say that Q1 is theta 1 and Q2 is theta 2. Okay, so there's L. So the first step, let's deal with Q1 first. So we have to find dl over d theta 1 dot. Okay, so we take our L term and we find all the terms with theta 1 in. Well, there's only this one, sorry, theta 1 dot, this one, and this term. Okay, so we've got three terms we've got to find. And so we've got this is m1 L1 squared theta 1 dot, okay, because the squared comes down to 2, and 2 times a half is 1. Then we've got plus m2 L1 squared theta 1 squared theta 1. Okay, again, the same thing. Squared becomes 2 times that. Okay, derivative of x squared is 2x, so that's what's happened, the half disappears. And then with this term, everything is a constant except for theta 1 dot. So we just write m2 L1 L2 theta 2 dot cosine of theta 1 minus theta 2. The next step is to take the time derivative of this, so that's d over dt of dl over d theta 1 dot. And so we have simply m1 L1 squared theta 1 double dot plus m2 L1 squared theta 1 double dot. And this is where it gets a bit complicated, because in this last term, think about it. What varies with respect to time? Well, we've got a theta 2 dot, that's going to vary with respect to time. The velocity, angular velocity of the second mass will vary with respect to time. Theta 1 will, and theta 2 will as well. And so we have to take the derivative of that term. And it's a product, there's two derivatives, so we use the product rule, and we multiply it out. So we've got plus m2 L1 L2 theta 2 double dot cosine of theta 1 minus theta 2. And then we've got to do the stuff inside the cosine. So we have a minus, because the derivative of cosine is minus sine. Okay. M2 L1 L2 theta 2 dot on its own sine of theta 1 minus theta 2. But then we need to take the derivative of theta 1 minus theta 2. So this is multiplied by theta 1 dot minus theta 2 dot. So we can stick that in there, in fact. Let's just put that in there to make it easier to read.
Sorry, Ben, I didn't quite follow that.
Okay. What we've got is, we've got this. Derivative of this one is simple. You just make the theta 1 dot into theta 1 double dot. The second one is the same process, theta 1 dot into theta 1 double dot. That's a 1. But for this term, we've got two things that vary with time. One of them is the theta 2 dot, okay, the velocity of the angle, the angular velocity of the second mass, that varies with respect to time. But the other thing that varies with respect to time is the angular difference between those two masses. And so we've got one term with something that varies, and then another one. So essentially we've got two functions that vary with respect to time. So you have to use the product rule, okay? Now the product rule, you should all be aware, if we've got u, v, and we take the time derivative of that, that's going to be u times d v over dt plus v times du over dt, yeah? That's the product rule, okay? And so we're just doing that with this term. And so we've got d over dt of m2 L1 L2 theta 2 dot cosine of theta 1 minus theta 2. Okay, well this is my u and this is my v, so that's going to equal m2 L1 L2, that's all constant. Then I've got theta 2 double dot cosine of theta 1 minus theta 2, okay, minus m2 L1 L2 theta 2 dot, so only a single dot because this is my v, okay, and then I'll take the derivative of this bit on its own. Well, that's going to be the derivative of what's ever in the brackets, theta 1 dot minus theta 2 dot, and then it's a sine of theta 1 minus theta 2. Minus sign, obviously the minus sign's there. So that's basically inserted into that bit there, okay? Yeah, does that make sense?
Yeah.
Yeah? So just remember that product rule. So now we have to find dl over d theta 1 without the dot. So we take all the terms that have theta 1 in, and all the terms with theta 1 dot and stuff are, disappear. So let's go back up to our L equation. So this term is a constant, that disappears. This term is a constant, that disappears. This term is a constant, that disappears. Here we've got a theta 1 in here. So we need to include that term. We need to include this term, but not this term. Okay, so let's do that. I'll deal with these two terms first, and then we'll go back to this one. So we've got cosine is minus sine. So we've got minus m1 g L1 sine of theta 1. Here, it's cosine turns into minus sine, so we've got minus m2 g L1 sine of theta 1. And then again with this term, cosine turns into minus sine, so this is minus m2 L1 L2 theta 1 dot theta 2 dot. Now it's all constant. This becomes sine of theta 1 minus theta 2. So now we've got our two terms that we can stick into Lagrange's equation. They're quite long and ugly, but fortunately we can simplify them somewhat. So if you remember, Lagrange's equation is this term minus this term, so let's write it out. Okay, the Lagrange's equation is d over dt of dl over d theta 1 dot plus, minus dl over d theta 1 equals 0. There's Lagrange's equation for this case. And so we've got this first term, that's up here, okay? And we've got the second term, which is this one here. And notice we've got a minus this term and a plus this term, so they actually disappear. And then lastly, we have this to deal with these two terms, so that becomes plus m1 plus m2 g L1 sine theta 1. So I'll write it out nice and neat. 0 equals m1 plus m2 L1 squared theta 1 double dot plus m2 L1 L2 that's the equation of motion of the first mass.
Is that L1 at the end of L1?
Yeah, L1 g sine of theta 1 because it's from this term here. Now, let's just go through the process again quickly. We find the Lagrangian, okay? We then go through, we find dl over d theta 1 dot, okay? which gives us this expression. You then have to take the time derivative of this term, d over dt of this term, which gives us this expression. Okay, this was an aside just showing you how I got these last two terms. So those two terms, stick them into there. We then have to find dl over d theta 1, which is this lot. Okay, apologies about this mistake, but you have to include the theta 1 minus theta 2, I believe. Okay, and then this is the Lagrange's equation when there's no damping and no force. Force is 0, r is 0, so then you stick this term minus this term, into this equation, and that will give you your equation of motion, which is at the bottom. I'm not going to go through for I equals 2, but I shall give you the answer so you can check yourself. So a nice little bit of practice is you take L and you do it for theta 2. And then you can check your answer by comparing it with this. 0 equals m2 L2 squared theta 2 double dot plus m2 L1 L2 theta 1 double dot cosine of theta 1 minus theta 2 minus theta 1 squared sine of theta 1 minus theta 2 plus m2 g L2 sine of theta 2. So that's the solution for when I equals 2, when you're dealing with theta 2, okay? So you can go through the process. I've given you L, and so you can go through the process to find theta 2, and hopefully it should match that.